So I'm going to talk about how we implemented IPv6 and why it took us essentially this long to get here. What is different in IPv6? It seems pretty simple, right? We just have addresses which are 128 bits instead of 32 bits. But the problem is that on any architecture, you can't really do meaningfully 128-bit comparison and assignment, which was easy to do with IPv4. eBPF itself internally is kind of 64-bit, but not 128-bit. And the next thing is that IPv6 headers have arbitrary size, which is not entirely true. The header itself is fixed size, 4 bytes. But it has something which is called extension headers. So the fixed size header is pointing to another header, which may point to another header, which may point to another header, which may eventually point to a TCP or UDP header, right? And that's a problem. IPv4 also has options, but it at least has a field that tells you like how much of the options. What's the total size of the header and where you find the next header. And the eBPF verifier just hates anything that is arbitrary size. So when I talked at the beginning about the technology, you write your program and then you try to load it into the kernel. Right? And verifier is the guard keeper. That's the gatekeeper that says, okay, I'm going to load it or not. And anything that the verifier can't verify, even though it's perfectly legal code, great code with no out-of-bounds accesses, it's just correct code, it may tell you, hold on, I'm not loading this. We actually had issues where the compiler produced perfectly correct code, but the verifier said no, just because the verifier didn't have enough context as the compiler on whether certain conditions hold in the code, and we had to change the C code so that the compiler produces different byte code, which then the verifier accepts. So yeah, as I already said, the verifier does checking, but that's the static analysis. And what if some of the bounds are only known in runtime? Normally, what we use is the TC hooks, and in TC hook, we get a packet. Internally in the kernel is the famous SKB struct, and we get something called __ SKB struct, which is kind of the mirror for eBPF. And the packet can be written, and we can read using some helpers, which I just talked about. So we can load the bytes, or we can store the bytes, or we can also write it directly through the SKB data pointer. So where we were at square one, about 5 years ago, our primary focus was performance. Right? And the main use case looked pretty straightforward. We see a packet, we do lookup with not tables, we run it through policy, we write a contract, there we go. And it was a fairly small program, and really everything looked good, and we were pretty optimistic about that. Correct me, Sean, if that's not true, but yeah, we were pretty optimistic about that. So we choose the direct packet access. Essentially, you have a pointer to the data, and you can read the data, and you can write the data in the packet. If we use the helpers, we would need to copy the data out in like fixed size chunks and write them back. And that's a little slower. And it seems like it's pretty easy to check bounds. It didn't really work for IP options, but we thought, okay, IP options are not really the main use case on the internet. You pretty much don't see IP options. It's a corner case we will fix eventually, no problem. One of the problems we realized was that sometimes you don't have all the data of the packet, but there was a helper that in case that we didn't have enough data, you can pull the data. And everything was fine. We essentially do the verification that we have the Ethernet header, we have the IP header, and then we have at least UDP size because that's good enough for TCP. In that size you have the TCP ports. Essentially 8 bytes of the L4 header. And the verifier was happy with that. We tried to access the IP header, the verified read from the TCP header. This verified read is verified because we know that we have enough data, so we can read the IP, and then we read the TCP port, and it's a verified read because it's going to be within this area. And essentially, it looked like you need one global verification, so at the start of the program you said, okay, is my packet big enough, and then you go. And that's the theory, but not the practice. There are many ways how the verifier can lose track of what's being verified because of how the compiler structures the code, what it puts on the stack and not. And typically helpers like update the checksum or expand the packet or trim the packet invalidate verification. So sometimes you just throw the verification here and there or the validation. At the square one, we have something very simple, and as I showed you in my previous presentation, it's not simple anymore. We have a whole chain of programs, and the verifier has problems of verifying massive programs, especially when it comes to complexity. The verifier essentially does exhaustive search of the program and bails out when it explored 1 million states, and it's surprising how a little tweak in a bigger program can trigger that. And eBPF comes with a pretty severe limitation that it has 512 bytes of stack space. And the compiler is in charge of the stack space unless you write assembly. And yeah, I don't want to do that. So we had to make a couple of new decisions. We had to kind of look back. We had to start grouping data in a single context so that it allows us to pass the data through the chain of programs. For that, the direct access was convenient because the packet itself, which is passed from the program to program by the kernel, also carries the data. So we didn't have to put the data in some external buffers and pass it that way. And BPF XDP load bytes was not available in, these helpers were not available in 5.4. So we couldn't use the same approach for PC and eBPF code. You can only use those helpers since 5.18. So and we use that helper in IPv6. So if you want to use XDP optimization with our eBPF data plan, you need to have at least 5.18 kernel. That also kind of highlights how difficult it is to mix environments, right? So what was the problem with verification for IPv6? So we thought that we just go with verifying that we have at least the IP header. Then we would get a pointer to the TCP header with IP options. We know how long is the IP options. And then we would take the TCP header, check whether it is within the bounds. If not, we will bail out. But hold on. Now we try to read the source port from the TCP header that we just verified that we have enough data for that. And the verifier said, out of bounds read. The problem is that we're verifying for 42 bytes of data. With options, we can have anything between 42 and 82, but the verifier doesn't know that. we know by specification that the IP header lang must be at least 5, so the header is at least 5 times 4 bytes, so it's 20 bytes. We know that, but that's written in the specification. So we need to add yet another verification that if we have IP header lang less than 20 bytes bailout, with that the verifier is willing to accept that if we have at least 42 bytes of data, but it's not sure about whether we have 82 bytes of data. And there's no proof, or the verifier can't be sure that we got a packet which has IP header lang that is telling us there's 82 bytes of data, but the actual packet has less data, right? So this is how conservative the verifier is. And this is why it is safe to load the code, but this is also the reason why it's kind of pain in the ass to write a code. I wasn't sure whether I should say it out loud, but it is. So with IPv4 options, we still use a direct access because it is a tiny little bit faster, but we copy out the headers if we see the options, and we have to pass the buffers in some maps, and there's quite a bit of restructuring in the code, and that on its own was quite a project to make it work. And the IPv6 extensions are sort of like the IPv4 options, but we don't know the lang up front. So with IPv6 parsing, we now go back to the helper. We're loading the bytes. We read the extension header. We read the next extension header, and so on and so forth. Until we find the L4 header. The verifier is happy that we copied the data into a statically sized buffer. When we find the TCP or UDP header, we can use the direct access to that buffer, which we write out back to the packet eventually. Why we do need to write it out back eventually is that if we modify the packet, we change the destination port for the service, then yeah, the packet needs to be updated. So now with the IPv6 code base, we essentially have two definitions of addresses. One is just a 32-bit int, one is 4 32-bit ints, and we compile the code either for IPv4 version or for IPv6 version. All we essentially needed to do once we resolve all the buffer excesses is to wrap all the comparisons and assignments in macros, and then we can maintain the code base just once, except the initial parsing, obviously. But the IPv4, IPv6 address is just 4 times bigger. Doesn't seem like much, but we have the limited stack space. And now the compiler comes into play, and we have the exact same code for IPv4 or IPv6, but the compiler is free to spill anything on the stack, even though when we have every function inlined, and even though we don't modify the data within that function, it just passes the arguments on the stack, and sometimes it can go so crazy that 4-byte values passes as like individual bytes. So the entire packet is not, the entire address is not 4 times bigger, but 16 times bigger. And to tweak that, again, took us some time. We now have to pass pointers. We also need to deal with ICMP. That's the corner cases. So if someone is trying to connect to a service and there's no backend for the service, we need to tell the client that there's no service, and so on. And with that, we kind of get to the point where we have to like reverse NAT the internal IP headers carried in the ICMP packets. Maybe, hopefully I'm not losing you here, but what is necessary to remember, or the takeaway here is that you have multiple layers of encapsulation in ICMP
and then we have to do the translation on multiple layers, and nothing is on a fixed offset. Verifier loves that. So we finally got over that, and we had to introduce a couple special programs. We had to chop off the programs into small sections so that the verifier doesn't bail out on the complexity of the programs. It doesn't bail out on that we have one function which we use in different locations for accessing different types of data. Yeah, that's pretty much what I said now. And we have to handle these corner cases like TTL, hop reduction. The network stack is not handling that now because we bypass it, so we have to take care of that. And from a pretty simple task, translate addresses and forward packets, you suddenly have almost like another implementation of the network stack. It is tuned for packet forwarding and routing, but there's so many corner cases that we have to deal with. For instance, source port collision on the host. Linux can deal with that. Say you masquerade a packet, and then you need to pick a different source and different port. And Linux kind of knows whether that port is available, right? It sees all the sockets, all that stuff. In eBPF, you don't quite see that. There are ways how to deal with these things, but it's kind of like to use your right hand to scratch your left ear, if I can put it that way. Simply, it's not straightforward. So here the data point becomes quite complicated. And so if I may conclude here, the devil is always in the detail. So it makes straightforward code very complex. It is not quite difficult to write a code, but really the nemesis here is the verifier. I've been to NetDev conference, which happened in Vancouver last fall, and there's lots of talk about eBPF. eBPF is really the hot topic, and it's great for many things, but the conversation always gets to the point like, but then the verifier, and everybody goes like, oh, verifier. Yeah, so you have to keep certain things in mind. If you do eBPF development, it's good to start from like grouping your state into a single structure. So once your program gets too complex, you can just put it in the map and pass it on to the next stage program. It's good to use exit instruction if you handle error conditions, because that makes the code simpler for the verifier to verify. That direct data access is quite tricky, and if we were to start again, now with 5.18 kernel, we might have started with byte load and store helpers instead of the direct access. So yeah, that's essentially I wanted to share why our own experience with writing the eBPF code and why it may have taken a little bit longer than expected to get to IPv6 state. But we got there, and in 3.28, it's going to be released as GA with dual stack. So if you guys use IPv6, please go test it out, use it, and come back with your experience and with your feedback. And we're happy to address any issues that you find, because that's essentially the most important contribution from the community, that you guys use the stuff and report back so we can improve it. If we don't know about that it's failing in the wild, we can't really improve that and fix that. So we're always happy to take issues, and don't be shy to report those issues. Thank you.
Thank you. Thank you. Thanks so much.